Okay, so this is what we will be creating, and let's get started. We will start with a geometry network. Let's call it sim and color it whatever you want. Let's dive inside, let's create a sphere, change the primitive type to polygon and increase the frequency to 10. Also decrease the uniform scale to 0.35. This is our sphere and we want some UVs on this. So let's create a UV project node. We have UVs on this sphere, but they are a bit disoriented. So we will change the projection type from orthographic to polar. And we want the polar ends to be on top and bottom. So let's change the rotation to 0. Let's create a UV layout node. And in UV layout node, come to target rectangles, and with the help of size here you can increase or decrease the size of the UVs. I'll keep the size to 1.1 by 1.1, and this is it. This is our base sphere. Let's use a null, call it base sphere out. We have our base sphere, and now we will create rest of the sphere objects. Now we will create a group of sphere through which our animated sphere will pass through and interact with. So let's create a grid for that. I'll template this grid, and I want this to be facing in the Z direction. So change the orientation to XY plane. Also change the size to 2 by 2. This is nice. Let's scatter some point on this. So we have scattered some points on this. By default it is scattering 1000. We will scatter 35 points. We are using the scatter node, by the way, if you don't know it. Now let's use copy to points node to copy this base sphere on all these scattered points. So this is it. We have scattered our base sphere on all our points on the grid, and this is looking nice, but there are a couple of issues here. First is that I want a couple of spheres here as well, because here at the start, because our animated sphere is going to come from the top and it will go through like this. So I want a couple of spheres here. And the other thing is that a lot of spheres here are intersecting with each other. We do not want that. So let's fix that with the help. Let's first fix the problem one, and I'll come to the scatter node and change the global seed to something that suits our vision. Global seed 4 is working for me because I get a couple of spheres in the beginning here, and our animated sphere will come from here and it will go down. So this is looking nice to me. Other thing is we want to fix the scale, so use a randomize node, and by default the attribute name is CD. We will change it to P scale. We will change it to P scale, and by default the dimensions are 3, but P scale is a float value, not a vector value, so we'll change it to 1. Let's change the minimum value to 0.6, and you can see the attribute randomize, the P scale is applied to all the scattered points here. They have all different P scale values, which is inherited by these spheres when we use the copy to point node, and this is looking nice. Let's view it from the front view. We have these spheres here which are intersecting with each other. Let's play with the value. I'll decrease the minimum value a bit, and let's decrease the maximum value also. Is it fixed? No, it is not. Sometimes you are going to face this problem, and maybe you are facing this problem as you are following along with this tutorial. Even if you change the minimum P scale value and maximum P scale value, there are some there are going to be some spheres which will be intersecting with each other. Come to the options in attribute randomize and you will find a global seed here as well. And let's work with that. And when you change it, you will find some seed, some value here where you will get a good positioning of all the spheres, where all the spheres are respecting each other's boundaries and they are not intersecting with each other. So this is the thing for me, and this looks nice, and I'll go ahead with it. I'll increase the p scale, minimum p scale value. Yeah, this is looking nice. Now we can create a group we will group all these spheres and we will call it something. So for that we will use a group node. Let's use a group node. We'll call it all spheres. That sounds nice. So we have group for all these spheres. We are calling it all spheres. They are grouped together, and let's use a null and we'll call it all spheres are out. All spheres out. That is it. Okay, so this is looking nice, and what we are going to do now is we will create some Vellum constraints for all these spheres. Okay, so we can move ahead and call and create some constraints, Vellum constraints for all these spheres. We will do that with the help of Vellum balloon configure node, because we want all these spheres to behave like balloon. So we are using Vellum balloon configure node. When you use a Vellum balloon configure node, you get Vellum cloth constraint and the Vellum pressure constraint. So as I explained in the earlier example, Vellum cloth constraint gives the object cloth properties, and we in the stretch section and the bend section we can control the stretchiness or the stretchiness of the object, this how stretchable the object is going to be, and the bendiness of the object, how bendable or how foldable that object is going to be. So these are the two properties that we will be controlling in the Vellum cloth constraint. And in the pressure constraint, we will control or maintain the amount of pressure that each object is going to have. So let's face it, let's see, this is our sphere, and we have to maintain this shape. This sphere needs to maintain a certain amount of pressure inside this, and we will control that with the help of this stretch stiffness in the pressure constant. And we can also control how much pressure we are going to generate in this sphere. So we can increase or decrease the pressure, and we can maintain the pressure. We can keep it pressurized. This sphere, we can keep it pressurized with the help of this pressure constraint. So let's play with these values, but first I'll bring the Vellum solver. So we have our Vellum solver, and let's run some test with all the default settings. Come to the forces and Vellum solver, and you will see that there's a gravity force, which is what we want. It is nice. Come to the collision, and we will create a ground section here. We will create a ground plane, and let's move it below, and we will create a ground plane just below all these spheres. So let's run this and see what happens now. Okay, so we have run that simulation enough, and you can see that the spheres are taking participation in the Vellum simulation, but they are not behaving like balloons or soft bodies, because the values are default. We haven't changed anything. So let's come back to the frame one, and we will play with the values. Come to Vellum cloth, and first we'll go to the geometry section, and we will apply all these constraints to our specific group, the group that we created, all spheres. So we will check our group here, all spheres. We'll do the same thing in the Vellum pressure constraint node as well. Apply it to all spheres. So all our constraints are going to be applied to these specific spheres. Vellum cloth. Come to Vellum cloth. In the stretch stiffness section, we will increase the stiffness to 1e plus 8, and that's because we do not want this sphere to be too stretchy. So we want it to be stiff enough, but we want some stretchability to this sphere, so that is not complete. We are not using 1e plus 10, but let's use 1e plus 8 for now. Come to the damping ratio, and I will increase the value here. Damping ratio, as I suggested earlier, what it does is it removes the energy from the simulation. What it is going to do is, when this sphere falls down or it take participation in the simulation, it is going to come to rest faster. That's what I want with this setting. If the value is too low, then it's going to take a lot of time for this to come to rest, to come to a still position. But I want this sphere to come to rest or still position lot faster than it would if I left it to the default value. So that is that. And come to the bend stiffness, and I want the spheres to be very bendy. So what I'm going to do is I'll use 0.001 value. The stiffness is 0.001 bend stiffness, and I'll increase the damping ratio here as well. So this is looking nice. Come to the pressure, and as I said, with the help of the pressure constant, we maintain the pressure inside the sphere, and we can increase or decrease the pressure in these spheres. So with the help of stretch stiffness, the stretch stiffness controls or maintains the amount of pressure, controls or maintains the pressure inside the sphere. So let's increase it to 1e plus 9. And the rest length controls how much pressure we can generate, or we can increase or decrease the pressure inside the spheres with the help of rest length scale. So I'll increase the pressure to 5. Just remember, stiffness maintains the pressure inside the sphere, this object, and rest length scale increases or decreases the pressure inside this object. So I have increased the pressure to 5, and let's run this and see our results. Okay, so we have seen enough, and the spheres are behaving like soft bodies, balloons now, and that is what we wanted. So it is a successful mission. You should give yourself a pat on your back. This is working. What we want now is these spheres are falling down. Okay, let's just fix this by decreasing or just removing the gravity force from here. So I'll come to the force Vellum solver, come to the forces section, and remove the gravity altogether. Keep it 0. We'll just uncheck the ground position as well. We do not want any ground here, so that is that. The thing is, even if you turn off the forces here, there's no force in your simulation, not even inside here. Let's play and see what happens. Okay, so we have seen enough, and as I said, even if we have removed all the forces here, we do not have a gravity, we do not have other forces, we do not have any other force. When we won on the second frame, all these spheres just get all the constraints values applied to them. Okay, so we have pressure here, we have increased the pressure to 5. In the second frame, all these spheres inflate and they get their pressure intact. They get the pressure that we have decided here. So when they inflate, they collide with each other and they kind of generate forces, and because of that they move on to different directions, and we do not want that. I do not want them to move to someplace else. I want them to keep their original position, and I want them to participate in the simulation, and I want them to keep their original position as well. So what we are going to do is we will use another constraint for that, and I love this constraint. I've been using it for a lot of projects, and let's use a Vellum constraint node. Come to the constraint type and change it to pin to target constraint. That is what we are going to use, and we want this constraints to be applied to our group. What group is that? We made that group here, and we will use that group here. So all the Vellum pin to target constants will be applied to this group, these spheres. Come to the pin to animation. So here's the main source. Change the pin type to soft. Okay, soft. This is what we want. when you turn it to soft, you get the stretch section and bend section activated. Stretch section and bend section gets activated when you change the pen type to soft, and this is actually what we want. They are like lever. You control whether the objects are going to take participation in the simulation, or they are going to stick to their original transformation or original position. And we control this with the help of stretch stiffness and bend stiffness. If I keep the value too high, then they are not going to participate in the simulation. They are going to stick to their original transformation, original position. And if I keep the value too low, then they are going to abandon their original position and transformation, and they will completely take participation in the simulation. We want the mix of that. We want a value where the spheres not only take participation in the simulation, but they also hold on to their original position. So for that, I'll use a position. I'll find a position like this. I will change the stretch stiffness to 1, and let's increase it a bit. I'll change the stiffness to 5. So stretch stiffness is 5, and come to the bend section. I'll change the bend stiffness to 0.0, maybe 0.001. Okay, this is it. Let's now see what happens when we run the simulation. Do they stick to their original position or not? And here we go. We have our spheres. They are taking participation. They are inflating, and they are participating in the simulation, and they are also giving respect to their original position. That is what they want. We want them to be in their original position. So this is it. I'll do one more thing here, and that is I want these spheres to collide with a grid. So I'll create a grid. This grid. I'll change the direction here. I'll change orientation to XY plane, and let's come to the side angle now, the right viewport. So what I want is I want this grid to be on the boundary here, somewhere here, so that when these spheres inflate, when they become balloons, they collide with these grids. So these grids are going to act like boundaries, or yeah, they are going to act like boundaries. I'll change the position of this grid to minus 1.5. Sorry, minus 0.15, or maybe 8. And I'll create another one, but this time we want to move it in the same, with the same amount, but in the completely opposite direction. So 0.18. We'll merge them, and now we will connect them to our Vellum solver, and they are going to behave like colliders. Let's see it from the front viewport, and let's run it. Okay, so far so good. Our spheres are inflating. They are keeping their original position, and they are also colliding with our grids. This is looking nice. All we need now is to create an animated sphere, which will come from here. It will pass through them and go down. So this is looking nice. Let's create our animated sphere. Okay, so to create the animated sphere, we'll use our base sphere. We will use a transform node. Okay, this is looking nice. We will change the uniform scale to 0.8, and I'll template these points so that we know where we have to transform this. On the position 1, on the frame 1, we will change the position. We want this sphere to be up somewhere here. Okay, I've changed the translation here in the transform to 1.5 in the y, positive y, and I want this sphere to come from here to go down there. On the frame 1, we will create a keyframe, and we can do that with the help of Alt plus left mouse button. You will have a keyframe. Come to frame number 105. This is looking nice, and here I want this to go down. 1.8 minus, yeah, minus 1.8. This is looking nice. We'll set the keyframe here on 105 minus 1.8. That is the position. So create Alt. Create the keyframe with the help of Alt and left mouse button. So we have our animated sphere. But this animated sphere is not going to work like a collider. We want this sphere to get affected by other spheres as well. So we will create Vellum balloon constants for this sphere as well, so that all of them can affect each other when they collide with each other, when they interact with each other. We want all the spheres to affect each other. So that is that. Let's create a group, and we want the sphere to be in a group as well. Let's name it anim sphere, and we will create now Vellum balloon configure. So this will create the soft body of balloon for this animated sphere. So the same drill, Vellum cloth constant gives the stretchability and the foldability to this object. The Vellum pressure constant creates pressure inside and maintains the pressure inside this sphere object. So we will apply these constraints to our specific animated sphere group. So come to here, come to the geometry and check the group anim sphere, and in the Vellum pressure constant do the same. Come to geometry group, anim sphere. Now we'll play with these values and see what will work. I think what I want is, I want this sphere to be to have enough I want this sphere to be not very stretchy. I want this to be a little stiff, but I want it to be stretchy as well, so I'm keeping the stiffness on the higher side. And let's change the damping ratio to 0.1 as well, just like we did in the last one. Come to the bend stiffness, and I'll keep the same values. Let's see if it works. 0.001, and I'll change the damping ratio to 0.1 as well. Come to the Vellum pressure for this animated sphere, and let's keep the pressure to 1E8, and this is okay. Let's change the pressure. This stiffness in the pressure constraint, this is to maintain the pressure inside the sphere, and this will increase or decrease the rest length. This will increase or decrease the pressure. Keep in mind, don't get confused here. Stretch stiffness in the Vellum pressure constraint maintains the pressure. Rest length scale in the Vellum pressure constraint increases or decreases the pressure. If you want to increase the pressure, play with this value. Okay. So this is that, and let's see what will happen. Let's take our Vellum solver that we have here, and we will test it out. Test the sphere. Connect it in the Vellum solver. Come to solver, and we will turn on the ground position, the ground plane. Let's turn off these templates, and I'll also turn on the gravity. Revert to default. You can type also, but I just did the revert to default thing because it says a default value. Now let's see what happens when this balloon falls down. Is it behaving like a balloon or not? Okay, it fell down, and it definitely is behaving like this.